Hey, right. Hi, guys. Okay, today we are going to be talking about the turning effect of forces, which will be on chapter 5. Right, so in this topic, there are essentially a few parts, right? So we will be talking about moments, we'll be talking about principle of moments, we'll be talking about center of gravity, and then we'll be talking about stability. Alright, to start off, okay, let me ask you this question. Okay, let's say for example, you are trying to open a door, right? So a girl is trying to open a door and she's trying to open the door at the door hinge over here, right? And then this guy, he's also trying to open the door, but he's trying to open the door over here, nearer to the door hinge. Which one do you think is easier to open the door? So it's easier to open the door here, right? It's easier for the door to be opened where the girl is, right? Where you are further away from the door hinge, right? When the distance from the door hinge is further away. Whereas for this guy, the distance to the door hinge is a lot nearer, and therefore it is more difficult for him to open the door. Right, so if the hand is nearer to the hand is placed near to the turning point over here, if the hand is placed near the hinge, a larger force is required. When the hand is further away, you will find that a smaller force is required. Okay, so at this chapter, by the end of today, you should be able to state the following. Number one, that the moment of a force is a measure of the turning effect of a force. Number two, you should be able to relate the moment of a force to everyday examples. And then finally, you should be able to state the formula for moment of a force being force times perpendicular distance from the pivot and use it to solve problems. Alright, again, okay, let's take a look at this, right? How would you want to balance the rubber ducky and the golf ball, right? Over here, you can see that you can probably make a guess that the golf ball will probably be heavier, right, compared to the rubber ducky, right? So there's a few ways that you can do it, right? One of it is actually to move the golf ball closer, right? When you move the golf ball closer, you will actually be able to balance the rubber ducky. Alright, now, yeah, so there you go. Okay, so this is me, just in case those of you who haven't seen me for some time and you miss me, there you go. Alright, okay, but actually the purpose is not so much to see my face, but rather to share with you this experiment that I did at home, right? To show you and illustrate to you, right? Okay, now we know that if I were to use my fingers and push this remote control, right? What will happen is that the object will move forward, right? So we have learned in the previous chapter that when you apply a force on an object, it may result in the object moving. Alright, but what if, let's say for example, I do the same thing, okay, but this time around, I fix this point over here, right? This finger, I fix it. So it will look something like that, right? So I were to push it, right? And then you realize that what happens is that if I were to fix this fixed point will be known as my pivot. And if I were to apply a force about the pivot, I will get a turning effect, right? This what's that remote control of mine will actually be turning, right? So I will get a turning effect. Now, likewise, if I do the same, right, but this time round I apply the force downwards like that, the object will actually turn in the opposite direction. So what I have is I will have something that looks like this, right? You will have your pivot, and then you will apply a force, and the force will be downwards, and it will cause the object to turn in this direction as well. Okay, so this brings us to the idea of the moment of a force, right? So in a moment of a force, essentially what it means is that when you have a force, it can cause the object to turn, right? So this turning effect of the force, this turning effect is known as the moment of a force. So we know from our earlier activity that the turning effect or the moment, okay, of the force will depend on a few things. Okay, number one, it will depend on the perpendicular distance of the force from the pivot, and it will also depend on the magnitude or the size of the force. Okay, which means that the larger the size of the force, the greater the turning effect. Likewise, the greater the perpendicular distance of the force to the pivot, the greater the turning effect. So the official definition for, or rather the scientific definition for the moment of a force is, it is the product. Okay, product actually mean multiply, right? Okay, to multiply something. Okay, so it is the product of the force, okay, the force, and the perpendicular distance. Okay, so you have the perpendicular distance from the pivot to the line of action of the force. Okay, I'm going to explain in a little while, okay, what it means by this. Okay, so what does perpendicular distance mean, right? So now, if you have a support, okay, and you have a beam and you have a support, so this support is also known as your pivot or your fulcrum, and you apply a force A over here. So the line of action of the force is here. Okay, simply, what does line of action of a force mean? It simply means in the direction of that force, right? So this is the force is acting downwards like that. So in the direction of the force, this is the line of action of the force, right? So the perpendicular distance that we are talking about and that we are interested in is the perpendicular distance from the force to the pivot over here. Okay, let's take a look over here. If this is the force, where do you think the perpendicular distance would be? So if you have guessed that the perpendicular distance from the pivot is from here to here, then you are absolutely correct. Okay, what about this one? Where do you think the perpendicular distance would be? Okay, so we draw the line of action of the force again, and then we draw the perpendicular distance. Okay, now this over here, where do you think the perpendicular distance will be? Okay, for force C. So if this is the force, the perpendicular distance will be from the force to the pivot, right? So all this is pretty straightforward. Now, what about if it's like that? If it's at an angle, then it becomes a bit more tricky, right? So the perpendicular distance is no longer from here to here, right? What you have to do is you must first draw out your line of action of the force first. Okay, so draw out the line of action of the force, and then from the line of the action of the force, you need to get a perpendicular distance from the line of action of the force to the pivot. So for this scenario over here, the perpendicular distance is from here all the way to here. Okay, so it's a very common mistake, okay, some students make, okay, to say that the perpendicular distance is still like this. Okay, this one is wrong. This perpendicular distance is only if the force is acting perpendicularly, okay, only if the force is acting perpendicularly like that or like that. Okay, then you can have the perpendicular distance to be this one over here. Alright, okay. Alright, so coming back, okay, to the definition of a moment and the formula for a moment. The moment of a force is essentially the force multiplied by the perpendicular distance from the pivot. And because the SI unit for force is in Newton, the SI unit for distance is in meter, the moment of a force is in the SI unit of Newton meter. Okay, so we say that the moment of a force, okay, it is a vector quantity because it has both magnitude and direction, right? So what will the direction of the force be then? The direction will either be in the clockwise or anti-clockwise direction. Okay, so what do I mean by clockwise or anti-clockwise? Okay, right, so next we want to talk about the clockwise and anti-clockwise moment. Okay, what does it mean by that? Okay, so basically when we look at the hands of a clock, okay, the clockwise moment means that the direction of rotation caused by the force follows the direction of a clock's hand, right? So how does a clock's hand look like? Okay, it will look like this, and then if the clock's hand were to turn, it will turn in this direction, right? So this is what I will say following the clockwise direction, right? Following the clockwise direction, following the hands of the clock, right? So all these will be clockwise direction. Okay, what if it was the opposite direction? Okay, if it was in the opposite direction, okay, let me try to change the color of my pen first, right? Okay, so if it's in the opposite direction like that, okay, if it's in the opposite direction like that, then this will be in the opposite direction of how the clock will actually turn. So this will be your anti-clockwise direction. Okay, your anti-clockwise direction, right? So when you have a force, okay, whereby you apply the force upwards like that, and it causes the force to move in this direction, right, which is in the reverse of the direction that a clock will actually move, this will be in the anti-clockwise direction. Whereas if, let's say for example, you have a force that causes the object or the beam to move in this direction, right? If it moves in this direction, it is moving according to how a clock will turn, right? So we say that this force causes the beam to turn in the clockwise direction. Okay, so let's take a look at this for a moment. Okay, let's just do a very quick example over here, right? Okay, so there are two things actually that you need to do. Okay, number one, you need to identify where the perpendicular distance is. Number two, you need to actually find out, all right, whether the beam will actually turn in the clockwise or anti-clockwise direction. Okay, so clockwise or anti-clockwise direction. Okay, so let's take a look at A over here first. Okay, so in A, where is the perpendicular distance? Okay, the perpendicular distance from the force to the pivot, right? So this is your perpendicular distance. So in which direction will this object turn? Okay, or this beam will turn? It will turn in this direction, right? So if it turns in this direction, we say that the beam will turn in the anti-clockwise direction. Alright, what about part B over here? Okay, so for part B over here, the perpendicular distance will be from here to here, right? So this is the perpendicular distance, and the force will cause the object to turn in this direction, right? So when it causes the object to turn in this direction, we say that this is a clockwise moment. Okay, this will be a clockwise moment. Alright, now, what about C over here? Let's take a look. Where is the perpendicular distance? You will realize that for part C over here, there's no perpendicular distance because the force is exactly at the pivot, right? So since there is no perpendicular distance, you will find that there is no turning effect over here, right? And in fact, if you do an experiment, okay, you will find that that is true, right? You will find that if you exactly put the force at the pivot over here, the object will not turn at all. Okay, the object only turns, okay, when you have the object only turns when you have a force multiplied by a perpendicular distance, which gives you a moment, which in turn will cause the object to turn. Okay, what about this one over here, right? Okay, will the object turn? Yes, okay, we know that the object will turn. Okay, the object will turn in this direction, so we know that the object will turn in the clockwise direction, right? So where is the perpendicular distance then? Right? We did this just now, right? So the perpendicular distance will be a bit tricky. Okay, for slanted forces like that, you have to first draw out your line of action of the force, right? Okay, and then the perpendicular distance will be from the pivot to the line of action of the force like that. Okay, this will be your perpendicular distance. Okay, so now let's take a look at some work examples, right? So let's say, for example, you have a boy pushing downwards at one end of a 3-meter uniform rod. If he pushes it with a force of 15 newtons, determine the moment he produces. So how are you going to do this question? Okay, so the solution is to find the perpendicular distance from the force to the pivot over here, right? So the perpendicular distance is 1.5 meters. So the moment will be 50 times 1.5 meters, which will give you a value of 75 Newton meter clockwise in direction. Okay, so you will need to have your magnitude and you will need to have your direction. Okay, what about this? Okay, you have another example. Okay, a girl is pushing or exerting a force of 10 Newton on the dell handle. So you want to find the moment due to the force exerted by the girl, right? So we are saying that the force exerted by the girl is here. Okay, so this is where she's going to exert the force at. So if she's going to exert a force there, the perpendicular distance will be the perpendicular distance to the pivot, this one over here, right? And if this length is 1 meter, we will say that this 1 meter will be the perpendicular distance from the force applied to the pivot over here. So to find what the moment is, we have to first determine the pivot, okay, which is the door hinges. We find the force, which we are told to be 10 Newton, and then we multiply by the perpendicular distance to the pivot, and we will get an answer of 10 Newton meters. Right? Okay, and then let's take a look at this example then. Okay, so what you have over here, okay, is you have an example over here which is found inside your textbook, right? Okay, so what you have over here is you have a weight, and this weight is actually 5 Newton. Okay, so this weight, which is actually equals to 5 Newton, is actually hanging from this beam, and this hand over here is actually acting as your pivot. Okay, the hand is actually acting as your pivot over here. Alright, so now what we want to find is we want to find the moment of the force by the weight about the hand, right? So this is what we want to find for part A over here. So in part A over here, to find the moment is equals to m equals to force times perpendicular distance. Okay, this is the symbol for perpendicular. You may choose to write this or not. This is entirely optional. Okay, but for me, I normally will write this down just to remind myself that the distance needs to be the perpendicular distance. Alright, now, so let's take a look at what is the force, right? The force will refer to the weight, which is 5 Newton. Okay, we have learned from the previous topic that when we talk about the weight, it's actually referring to the gravitational force acting on the object, right? So the force is 5 Newton. Okay, what about the perpendicular distance? Okay, the perpendicular distance here is from the 40 cm mark all the way to the 15 cm mark, right? So this is 40 minus 15 equals to 25 centimeters. So this will be 5 Newton times 25 cm. You will get a value of 125 Newton centimeters. Right, now, you can either leave it like this, or if you want to leave it in the SI unit, right? I know some of you, you know that. Okay, some of you will say, hey sir, but the SI unit for moment is the Newton meter, right? So if you want to leave it in the unit of the Newton meter, that's fine also. Okay, but what it simply means is that your perpendicular distance needs to be given in the unit of meters. And how do you do that? Is by taking the perpendicular distance in centimeters, dividing it by 100. And then you will get a value of 1.25 Newton meters, right? So this will be the moment of the force in its SI unit. Either way is fine. Okay, either way is fine, especially if the question does not specify, right? Okay, now for part B, okay, you are told that now you want to actually move the weight to the 5 cm mark, right? To the 5 cm mark means over here, right? This is the 5 cm mark over here, right? So now, what will be the perpendicular distance? The perpendicular distance will be from the 40 cm mark all the way to the 5 cm mark over here, right? So it will be 40 minus 5 will be equals to 35 cm. So to find your moment, okay, to find your moment, you need to take your force multiplied by your perpendicular distance, and this will be 5 Newton times 35 cm, and you will get a value of 175 Newton centimeter. Or if you were to give it in the SI unit, it will be in the value of 1.75 Newton meters, right? So either one is okay. Okay, either one is okay. So now you can see that just by shifting the weight here, okay, because of the larger perpendicular distance, it results in a larger turning effect, right? So for part B, okay, it results in a larger turning effect, right? And because it results in a larger turning effect, what it means is that it makes it more difficult for you to hold on. Okay, makes it more difficult for you to hold on to your beam because of the larger turning effect due to the weight and the moment, okay, about the pivot. All right. Okay, so this example is actually in your textbook. Okay, so you can actually go back to your textbook, okay, and look at your answers from there. Right? Okay, so in summary, very quickly, okay, we have learned that the moment of a force. Okay, so what is the moment of a force? The moment of the force is the turning effect of a force, right? So when forces, okay, are acted on an object which is pivoted, especially, okay, when it's acting on an object which is pivoted, right? This is the pivot. Okay, I can either draw the pivot like that, or I can draw it like that. Okay, this is to represent that I'm holding on to this point over here, right? And when you apply a force, okay, it will result in the object to turn, right? So this turning effect of the force, this is the moment of the force. And the moment of the force depends on two things. Okay, number one, it depends on the force, how big the force is applied. Number two, it depends on the perpendicular distance from the line of action of the force to the pivot, right? The perpendicular distance over here. Okay, so this is one. Okay, this is the one thing that we have learned today. Okay, the next thing that we have learned is that the turning effect of a force can either be in the clockwise direction or it can be in the anti-clockwise direction, depending on how and where you apply the force on the object. All right. Okay, so I hope you are able to follow, okay, and understand these first two concepts first. All right. Okay, so I will be doing the rest of the chapter in due time. Okay, so next I will be giving you some practice questions to try, and I hope you'll be able to do them. If you have any questions, you can always WhatsApp me. All right. Okay. Take care.